Vamos a empezar. Es un placer tener, y un honor también, tener aquí al profesor Heyman, que, como sabéis, es uno de los teóricos más importantes en el campo de las estructuras y que, además, desde los años 60 ha arrojado una luz inesperada sobre el comportamiento de las estructuras de fábrica, que es de lo que va a hablar hoy. Así que, nada más.
Thank you, Professor Huerta. It is a very great pleasure for me to be here again as an engineer, addressing mainly architects, I know, and this is a totally non-mathematical exposition of engineering, although there is one horrible equation, which I will show in a slide later on, which I will try and explain, and I do it for a reason. The first thing we must realize about engineering is that it is impossible really to obtain an exact solution to any problem in engineering. And in structural engineering, the situation is the same. We can never be certain that we have a correct answer. And the only way to make any progress at all with a problem is to make some assumptions. Now, I'm going to talk this morning about thin shells, and more generally about structural engineering and more generally about masonry. But in the question of thin shells, we make an assumption of thinness, so to speak. That is, that the shell we are considering is something with very small thickness compared with the span. Or really, a better measure is not the span. For example, the dome of St. Paul's Cathedral here spans some 43, no, that's wrong, 37 meters. The radius, it is not a hemisphere. I'm talking here of the innermost dome here, surmounted by a conical dome, also in masonry, surmounted by a timber dome on the outside, so there is a triple dome here. But the innermost dome, which we will start with here, is not really a sphere. It varies, as we will see, but you can assign a radius to it, something like 23 meters as the radius of that sphere. I picked the value 23 because it is convenient. The thickness of the dome here, marked in feet and inches, is in fact 460 millimeters. Conveniently, the radius divided by the thickness is 50. And the number of 50 defining the thinness of a structure, it certainly is thin. In fact, membrane theory, about which I will talk a little this morning, assumes that the ratio of radius to thickness is 20 or more, so that 50 is certainly thin. And we make some assumptions there, which we must be very careful of because they can be misleading. I say that the innermost dome is not a sphere. It, in fact, never becomes vertical. As you can see, the lines here slope downwards, and we will explain that. It is the only dome that I know on this scale, built with that sort of inclination of the supports, although, of course, it was a device very much used by Gaudí. For example, in the Sagrada Familia in Barcelona, there are inclined columns and so on, somehow following the forces. Again, we will talk about that later on. Now, this is a very different type of thin shell. Candela, a restaurant in Mexico, and of a very different form from the dome that we've been considering. The dome, if you're standing inside it, and we will come back to this again and again this morning, if you're looking down the church, the dome has a curvature in a direction. If you're turning the other way, the dome has the same sort of curvature. This sort of shell evidently has different sort of curvature in it. arrangement. And this is the reason why I shall show this horrible equation in a minute, because it will try and express mathematically what the difference between this sort of structure, which is like a saddle on a horse, for example, or a cooling tower. Various structures have this sort of arrangement, notably, and again I will show slides of this, the fan vault in English architecture. These vaults of candela are very much thinner than the 50 we quoted for the radius to thickness for the dome of St. Paul's, which incidentally is the same sort of figure that you have in the construction with 2 bricks in Catalan vaulting, for example, in the so-called timbral vaulting that you have very much in Spain. Again, a figure of about 50 is right. Candela's thicknesses are 100, 200 or something. They are very, very much thinner. And in addition, this cannot be a masonry vault. It is reinforced concrete with steel bars taking tension, and it's not possible to obtain solutions to our famous equation, not involving tension, and as you know, masonry is a material which is really unable to take tension. I must stress this again later on in a minute. Here are some sketches of the candela vault, and it's evident here and there that although these are sketches showing the sort of shapes that can be derived, there is some sort of mathematics going on here, and that's even more evident in this picture, where some sort of grid system has been set up to try and describe this shape mathematically. Now, how, as an engineer, would we set about the analysis of a vault like this? Well, we would look at the surface and study a little patch, perhaps enclosed with those 4 lines there, and try and determine what the forces are. We would set up a system of axes, a horizontal plane, x and y, vertical distance z. The distance from that plane to the shell gives the depth of the shell below the surface at any point. And then we would look at a little patch on that shell and assign forces. And this is where we're beginning to make some severe assumptions in our engineering analysis of this particular structure. These P's represent the weight, the forces acting on this little element. This is evidently the self-weight. This might be perhaps due to wind or something like that. In general, there will be 3 components of force there. They need not worry us, they need not come in. But what those forces do is to produce stress resultants, very much like the 2-dimensional stress one gets in elasticity analysis. That is, you can have a pull in one direction, the y direction, a pull in the x direction, and a shear force on the surface there. But most importantly, the theory assumes that there are no forces transmitted through the shell across these surfaces. These are the only forces acting there, and that there is no bending of the shell. So this is a severe restriction on the analysis, which we must take account of at the end of the story here. What we can do with this is to resolve forces horizontally, vertically, and so on, take moments, and establish the usual, really rather simple stress equations which result from this series of fine assumptions that are being made here. We are only going to consider these equilibrium equations. Nothing else is going to enter into the analysis throughout this morning. And this is in severe contrast to the way a structural engineer usually thinks about a structure. In general, if you write the equations of equilibrium for a structure, a frame, shall we say, or a reinforced concrete building, one finds that these are not enough in order to determine the state of the structure. You have to make some other statements. The other statements that are made are, in general, some statement about the material properties, the elasticity, shall we say, how much the material stretches when it's stressed. And finally, one must write the so-called compatibility conditions. And normally, these merely state that the structure is sitting on supports, and we know where those supports are. There are boundary conditions placed upon the solution, which must enter into the analysis in order to obtain the final solution to any particular problem. These boundary conditions are what we call displacement boundary conditions. That is, they define movements or non-movements, rigidity, at the boundary. We have nothing of that in our membrane analysis of shells. We are dealing only with equilibrium. We are not dealing with any material properties, with any elasticity. We're not dealing with any displacements. And that is, any solution that we might find to our equation will result only from this consideration of forces on the structure. And there is the horrible equation which we have to solve in order to determine the stresses which are acting upon our candela vault, shall we say. First of all these terms on the right-hand sides in P, those are the loading terms acting on a particular structure, and they need not concern us at all here. This is a partial differential equation, second order, for those of you who know mathematics, to determine this function phi from this equation. And once the equation has been solved to give the value of phi, then we know what those stresses are that we showed on that previous element. The pulls in the two directions and the shear stresses can all be determined from that. And this equation can indeed be solved for any particular shape of vault. And the shape of the vault, remember we set up these axes Z and X and Y. The shape of the vault is contained in these terms here. Again, this need not concern us deeply, but I'm going into it because it is the signs associated with this term and with this term which determine the whole characteristic of the solution. This essentially is the curvature in the x direction, the amount of curvature of the vault going like this. The other one is the curvature in the y direction, the curvature like that. And if we are standing inside a dome, then the curvature there and the curvature there have the same sign. But if we are standing inside a candela vault, that restaurant in Mexico, then the curvature in one direction is like that, but the curvature in the other direction is of the opposite sign. And that means that these two have differing signs, and the whole solution of the equation changes dramatically accordingly. Let's just illustrate what we're discussing here rather dramatically here. The dome-like structure with curvatures the same in both directions is, of course, corresponds to this. And this is the analog of the candela shell, where the curvatures are plus in one direction and minus in the other direction. This is the intermediate case, which is important, actually, for Gothic architecture, where we have zero curvature in one direction. We've got a flat surface there. The principal curvatures, this way and this way, multiplied together, are called the Gaussian curvature. And if the Gaussian curvature is positive, then we have this sort of structure. If it is negative, we have this sort of structure. And if it is zero, we have the cylinder, or as it turns out, the Gothic quadripartite vault. Now, according to our simple theory of the equations, that horrible equation which I just removed from the, from the screen, if we are dealing with this sort of structure, and shall we say we put a point load somewhere on the top there, some disturbance, that disturbance will dissipate very, very quickly. It will spread throughout the structure and diminish as you get farther from the point of application. A practical application of this is in the ordinary hen's egg. An ordinary person like me finds it difficult to take a hen's egg and try and break it by pressing between my thumb and forefinger, because the forces spread out through the shell and are accommodated reasonably comfortably. It's obvious of importance to birds which lay eggs. Those eggs can be tilted and dropped, perhaps, and they will not break necessarily. By contrast, if we put a point load on the edge of a shell with negative Gaussian curvature, then that force, in theory, can be transmitted unchanged. It just goes straight through the shell and does not get dissipated at all. There is no dispersion, as there is with the egg, but a concentration of force. And this, of course, is where one has to question one's assumptions that one is making about the behavior of these shells. It seems unrealistic to suppose that you can transmit a force completely unchanged through a complex structure. And this is easily explained because, of course, if we've got a force traveling down through a particular fiber in the structure, the real material, which is elastic, will compress, and the material adjacent, not subject to force, will not be compressed, and there's an incompatibility of strain between a portion of the structure which is theoretically stress-free and one which is stressed due to this load and one which is stress-free. And so that force will, in fact, dissipate. But the tendency is right. The tendency is for the forces to dissipate really rather slowly in that sort of structure. Well, now, an example in Gothic architecture is the fan vault. And you can see that in such a vault, the curvature in one direction is in one direction, but it's negative in the other direction. This is the Gloucester cloister of about 1450, one of the earliest uses of the fan vault. The geometry, just to stress this, it is fairly clear of the fan vault structure, the way that we get this plus and minus curvature compared with the normal sort of barrel that one gets in a dome-like structure or in a barrel vault configuration. And this is one of the most spectacular and, in fact, the biggest fan vault that was built, just over 12 meters. This is King's College in Cambridge. Rather curious arches, which usually do not occur in fan vaulting. This was because when the building was started in about 1460, there was no intention of using a fan vault, but it was only completed 45 years later, and they decided to have a change of style and to impose the fan vault on the top. But the arches were already there implicit in the mouldings, and the architect ran these arches through. And it is not displeasing. It divides the structure up into passages. Let's leave these complicated matters for a moment. This membrane, this, if you like, two-dimensional analysis, and go to the one dimension, or really, let's go to the arch to see how that behaves. This is a picture by Salvador Dali. I don't know what he was intending by this, but it's clear, of course, that this is a ridiculous structure. It cannot stand in that way. It must be thrusted against by something on the other side if we to have a viable structure. And it is perhaps Dali just stating that an arch cannot stand without having some sort of thrust. That is the equilibrium, and we're dealing, remember, totally with equilibrium this morning. The equilibrium of such a masonry construction compels the arch to develop forces within itself. There is no escaping from the thrust generated there. And just to remind you something that you very well know, first of all, the arch is really rather difficult to build. In order to build a voussoir arch across a river, shall we say, You have to have elaborate centering or to support all the stone voussoirs, and until the keystone is in place, you haven't got a structure at all. When you've completed the arch, you can take the centering away, and immediately the arch must experience that thrust that we were talking about. And it starts pushing against the riverbanks, and the riverbanks give way slightly. And here we get the characteristic behavior of masonry, which all workers really assume now, that we have a material which is incapable of taking tension. Something has got to crack. If you impose a spread in the abutment, implied by this very much exaggerated second figure here, and cracks will develop in this way, hinges, if you like, again, grossly exaggerated, though if you go under a masonry bridge on the river and look up at the centre, you will very often see such a crack, indicating that movement has taken place. This indicates somehow the way the forces are transmitted, this thrust within the arch in this configuration. We must go through this point here, that's the only point of contact, and through this. And so the resultant of the forces passed from voussoir to voussoir as we go down in the arch, follow some such trace as that. Well, this is not a lecture on arches, but the fact is that if you have an arch of any reasonable thickness, then there is an infinite number of ways in which you can transmit the forces within the masonry. And here are three possible sketches. There's nothing new in this lecture. This was a picture of about 1840 in England at the Institution of Civil Engineers, somebody demonstrating how arches worked. And there are three possibilities sketched there. There's an infinite number in between all of these, and these were demonstrated by the lecturer at the time. As the arch becomes thinner, of course, it is not possible to accommodate any shape, and this, in fact, sketches the minimum thickness of arch, which will only just accommodate the forces there like that. And here you get a mechanism of collapse of the structure. The three hinges that we got just by the abutments moving apart do not in any sense connote ruin of the structure. They are merely an inevitable consequence, indicating that some movement has occurred at some time. Let us now get back, having that little brief introduction, if you like, something that I'm sure you very well know about the behavior of masonry. Let's get back to the, to the shell structure, the membrane analysis, and let's consider the dome, the hemispherical dome, and apply our master equation to a pure sphere of that sort. Of course, the equation is grossly simplified if you've got the simple geometry of a sphere, and the solution comes out very, very easily and quickly. And along a cut halfway across the hemisphere, you have got stress resultants which are compressive from the crown round to about 50 degrees here. But then they start becoming violently tensile. And this is not admissible, therefore, for a solution if we are looking at a masonry dome, which cannot take tensile stresses. Something has gone wrong with our analysis, with our assumptions perhaps, and this is where one must begin to look at the beginning assumptions of the whole theory. We have assumed that our membrane has got zero thickness, and so the forces are compelled by the geometry of the sphere imposed in this way. In reality, just as we could find a line of thrust within an arch, providing it had a certain thickness, so we must allow for the fact that a real dome has got a finite thickness, and the forces can depart from the constraint that they should follow the spherical surface, and they can move within the thickness, and providing you give the dome a certain small thickness, about 4% of the radius actually, then the forces can be contained. So that if we considered a domical cap, not a complete dome, but defined by an angle alpha there, as long as alpha is less than about 50 degrees, 51.8 degrees, we can get compressive stresses everywhere within the masonry. But beyond 51.8, we must provide some finite thickness for the shell in order to accommodate the forces within and so that they all stay compressive. And this is just a plot of the minimum thickness required, going up, as I say, to a thickness of about 0.04 or R over T of about 25. Still a thin shell here. So it is relatively easy, therefore, to find solutions for any practical dome. Now, just as our two-dimensional arch thrusting against the riverbanks exhibited cracking, so here, in a grossly exaggerated way, is what happens to a dome sitting upon a drum, and the drum perhaps expands in diameter a little bit so that the supports give way. The dome must inevitably crack, and as I say, shown grossly here are cracks which would allow the dome to move outwards in diameter. It's important to realize that this cracking, just as for the arch, are caused by movement and not by stress. We saw those tensile stresses on the previous slide near the base of the dome. But as long as the dome does not increase in diameter, there is no possibility of cracking due to stress. It is the movement which causes this. The stresses can be quite low, but nevertheless, this cracking will occur. And of course, again, as you very well know, Polleni, you probably can't see these very well from here. Polleni, in his study of St. Peter's in Rome, found such cracking. I can see one here. Perhaps more visible to you are cracking as they approach the base of the drum coming down here. The movement apart there indicating cracks and the whole spread of the structure. And Polleni made a brilliant analysis of this, dividing the membrane of the dome, if you like, into a two-dimensional arch structure. The cracks had already divided the structure into that sort of grossly exaggerated picture we saw before of orange slices side by side. And Polleni said, let me consider one such slice leaning against one on the other side. Let's consider an arch cut out of the dome of St. Peter's. He knew all about the way forces were carried within an arch. See if I can find a set of forces lying within such a structure. And what he did was to make a drawing of the cross-section, to divide that cross-section into imaginary voussoirs, to compute the weight of each of those voussoirs, to make a ball corresponding to the weight and to hang those balls upon a chain, and to observe experimentally, then, what the line of thrust would be, that is, the hanging chain, which, when inverted, will give you the way the forces are carried within the arch there. So that he finds this particular geometry here, turns this up, and says that is the way the forces are carried in compression rather than in tension in the arch. And all this is perfectly sound thinking. It's difficult to see this line, but it does in fact lie within the masonry, and that, said Polleni, is what I wish to know about this structure, and hence the structure is safe. For the last time, let us go back to that horrible equation. Again, let me remind you, these are terms which don't concern us in this analysis. They are the loading terms on the structure. We can solve this equation the other way round. Supposing we follow Polanyi and say that in our solution we will impose a requirement that there are no forces carried round the hoop direction. That is, the cracking in the dome has already divided it into separate portions so that we've only got forces coming down the meridian. So we are defining the stress resultant system. We are defining, in fact, this function phi, which gives us the stresses. We can then solve this equation to give us the z, the shape of the structure which would correspond to that assumption. Right, so we're dividing the structure, no hoop forces. That must correspond to a particular shape of structure. And it's a horribly complex equation, actually, which gives a horribly complex solution. But it is very, very close to a solution guessed at by Robert Hooke in the time of Newton for the shape of the perfect dome, which was not a parabola, y equals x squared, but a cubic parabola, y equals x cubed. And in his diary, he says that he told Christopher Wren of this discovery of his for the shape of the perfect dome, and that is the way that Wren designed the dome of St. Paul's Cathedral. This is one of Christopher Wren's sketches of about 1690, of his studies of possible domes. This wasn't actually as built, but it applies to this particular dome coming down this line here. And he has set up axes 1, 2, 3, 4 in that way, and dimensions down this way. And starting from this point, moving through a unit distance, we would come 1 cubed down 1. Moving through 2, we would come down 2 cubed, which is 8. Moving through 3, we would come down 3 cubed, which is 27. And then finally to 64. And this shape here follows Hooke's cubic parabola, and it follows almost exactly this rather complex solution that I was hinting at one can get by looking at the basic equation. Let's move on to a structure, as I said, with zero Gaussian curvature, the quadripartite vault, where one surface is flat in one direction and curved in the other, and we're intersecting along the groins, reinforced in Gothic, of course, by ribs. One can apply this same sort of theory to this structure, but let us first look at the practical behavior, which will give us some hints as to how we might start on this. If one looks at a practical quadripartite vault, one sees cracks of various sorts. There is this crack somewhere near the center. There's a crack a meter or two in from the end, and another crack at the end of the vault. And these occur very regularly in almost all vaults, and they are due to movements, again, not to stresses. And they occur because, considering first just a barrel vault built, this is actually roughly Gothic dimensions, the thickness corresponding to the span. And this is a two-dimensional arch, a barrel of uniform cross-section moving into the picture plane there. Notice that in order to get the line of thrust, the inverted hanging chain, that will never come down vertically here. It will spread out, and you need the fill in the vaulting pockets in order to take the forces out of the structure. Right, we build this vault. The vault starts thrusting against the flying buttresses at this edge. The edges give way slightly, the span increases, and we get this cracking occurring, as we saw before with a simple arch. Now, let's go to the proper problem. That is the same cross-section here, but now with another vault running north-south, intersecting. We've got the same expansion, the same 3 cracks there. There's not enough material to fill this increased span for the vaults running east-west, the north-south vaults having expanded. And that is, this hinge is a hinging crack, but these are complete separations of the material, and you can stand on top of the vault and put your hand through these holes to confirm that there is separation. So these are free of stress, if you like. They're just holes in the vault. This is a hinge. This means that the edge here has pulled away from the supporting structure. There is a gap there against the masonry. There is no force acting on the edge of this vault, no force acting in this direction, and this is one of those occasions when the forces are transmitted theoretically unchanged through the vault. So if there is no force acting on the edge there is no force at all acting along the flat direction of these vaults. All the forces must go down the curved lines, and Paul Abraham had the idea of a marble sitting on the top here, a little ball which rolls down, which would indicate the way the forces are carried. The forces down here and the force down there meet on the groin, on the ribs, and so on. And you can calculate in this way, very simply, by use of these simple ideas of equilibrium, how these forces are transmitted. And further, of course, one can immediately say that if there are no forces being transmitted across here, it would be perfectly legitimate to slice the vault in that way and just to consider parallel sets of arches, and the forces in those can be computed from conditions of equilibrium very simply indeed. Well, let me finish up by saying a little about fan vaults, which are good examples of these vaults, these shells of negative Gaussian curvature. This is Peterborough Cathedral. There are only 4 big fan vaults in England, in the world. They were all built within about 20 years, around the year 1500, for a reason which I will try and explain in a minute. This is the smallest at about 8 meters span, and those are the fans, indicating the complex geometry, and incidentally, also implying the very complex cutting of stones. The stereotomy of this structure is enormously complex in order to construct such a doubly curved membrane, if you like, to actually put it together, compared with the idea of a dome of just 2 bricks thickness, which you just lay one on top of another, the timbrel vault construction. This is very, very much more elaborate, and one of the reasons, I'm sure, that there are only 4 vaults in existence, and then the whole idea of that sort of architecture was abandoned, was because it was just very, very expensive to construct such a particular vault as that. This is Henry VII's chapel at Westminster, with very, very fancy architecture indeed. There we have got an arch which is, in fact, somehow hidden within the structure. You can see it starting from the edge here, but it then disappears through these pendants and goes on top of the vault, all this being one stone, actually, the vault itself and the arch cut from a single block. The pendants, well, we won't go into this is another lecture altogether, but these pendants rely from their strength on the fact that the material in a single stone, of course, has tensile strength. This is just a single voussoir, if you like, in the arch, which has been elongated here to give a decorative and rather magical effect to the whole structure. But the complexity of the stone cutting is still there. And there is a view looking up at the main chapel in Henry VII Chapel. This is King's College Chapel. Again, very, very elaborate, fancy work there. Let us look just very, very briefly, to wind up with, at the construction of a fan vault. This was a study of 1840 into King's College Chapel, which we just saw. As you can see, this is upside down, this slide. The author was concerned with the way the stones were cut and how the whole structure was fitted together and so on. And he's constructed a complete fan in this way, illustrating the complexity of the stereotomy. Supposing on that we use this technique of slicing, instead of looking for a complete membrane solution, let us, in the way that Polenyi did in the Dome of St. Peter's, divide the structure by imaginary cuts through the masonry and attach the stones to a chain carrying the weight, and so we can replace the forces by these lines there. Then if we turn that upside down, what we get is a picture of a sliced fan vault whose forces are concentrated compressively along lines like that, separated one from another so that there is no interaction between these solid lines there, and we can cut the whole vault in half there and throw this half away, and what we've got is just a picture, an analogy, a simplified version of the fan vault as it actually acts. And this does illustrate, actually, the second reason, I think, why fan vaults were abandoned. In building such a vault, the forces, the compressive forces along these lines build up and up. The equilibrium condition is inexorable. One must have compressive forces there, and they must come from somewhere. And there is no escaping from the fact that in order to build such a structure, every stone you place must be supported from below until fans meet each other on the opposite side of the church and can push against each other and so generate these compressive forces. What I'm saying is, just as for the two-dimensional arch built across a river, you have to have centering until the keystone is in place. You cannot remove that centering. So, in building a fan vault, you have to have extremely complex centering, which cannot be removed until you completed the whole structure from both sides and going down the building, and the components start interacting. Only then can you remove this expensive centering and take it away. And it is the cost of the centering, which was very expensive indeed, it still is expensive, and the cost of the elaborate stone cutting, which I am pretty sure led to the death of the fan vault. This is the fourth big fan vault. This is Bath Abbey, just about 1500. They were all built by the same group of architects, working together, exchanging information. There are records, for example, in Cambridge, of the architects from Westminster Abbey coming up to Cambridge and consulting about the building of the fan vault at King's College Chapel, and so on. It was well known that they got together. Well, let me try and summarize what I've been saying. The membrane equations, or the even simpler sliced equations, which we been dealing with recently, but let us think of the membrane equations, are purely statements of equilibrium. And they give unique solutions which must, however, obey certain boundary conditions, compel certain boundary conditions, not the displacement boundary conditions of conventional structural analysis, but force conditions. That is, our sphere sitting on a plane, for example, requires support of certain magnitude along a certain periphery. And the equations compel those forces to appear if you are to believe the equations. What then happens if, for example, the surface is uneven and is unable to provide the support required by the membrane equations? Then one must have to look at the assumptions one has been making. Strictly speaking, the solution is no longer valid. In practice, what happens, of course, is that the shell will deform slightly, that is, the geometry will change, and we've assumed a constant geometry in the membrane equations. The elasticity of the dome will allow certain displacements to occur, and we have ignored displacements. And of course, in fact, the dome will settle down in a slightly different shape from the one we have assumed. And we must question, as engineers, whether those small displacements from our theory are sufficient to invalidate the whole theory, whether we can rely on the values of the forces we've determined from the simple theory, and so on. In general, if the displacements are small, in general we can rely on them, but we must always question those assumptions. Secondly, I've stressed the fact that the theory, well, this is in common actually with much of structural theory, but that the membrane theory assumes a shell of zero thickness everywhere. And in fact, our real shell has got a finite thickness, and this enables different force systems to be established which depart from the geometry we have assumed. That is, the forces can stray from the surface of a sphere into something else in order to achieve equilibrium. So that again, we must look at the tyranny, if you like, of the geometry we've imposed and see how far that can be relaxed. And I've talked finally about the difference between the dome-type structure, in which, in theory, forces get dissipated really rather quickly, and anomalies are accommodated easily, as compared with the candela-type structure, where anomalies are not so easily dealt with, where if we do get a discontinuity in force, that might lead to severe disturbance of the structure. One has to be careful, for example, in constructing a cooling tower, and that was the left-hand structure that we saw on those three shapes there, about the way that is supported on the ground, because an anomalous force there might cause serious damage. But above all, the difference between these shells of positive and negative Gaussian curvature is that a dome is relatively easy to build without too much artificial centering in order to support the masonry. As Brunelleschi stated in Florence, and of course he was not believed until 18 years later, but he did manage to build the dome of Santa Maria del Fiore without too much centering, as opposed to the fan vault, where the equations imply that not only are the force systems going to be different, with a tendency, almost requirement, that you are going to have tension until you completed the structure, and the fact that construction is going to be very difficult indeed compared with Brunelleschi's dome. Thank you very much.
Thank you very much. ¿Hay alguna pregunta? Well, thank you so much.